In the last class, we were talking about the boundary crisis. Just to briefly recapitulate where we were, we said that if there is an attractor, that could be a periodic attractor or a chaotic attractor, whatever, but supposing there is not only one attractor, but there are more than one. And also we had considered the attractor at infinity, the instability condition, that means the condition under which the system will collapse, the state will run to infinity, that also as an attractor. So, if that is so, then there would be some kind of a basin boundary. Suppose there is the attractor at infinity, and supposing here is some kind of a stable attractor. That stable attractor could be a stable chaotic attractor also. If with a change in the parameter, this chaotic attractor moves in position, also the basin boundary would move in position, and if it so happens that the chaotic attractor makes contact with the basin boundary, then what will happen? Then suppose it comes somewhere, say here, then if you start an initial condition somewhere here, it will still go there, it will still go on making its iterates within this, but at some point of time it should fall here, a point that is outside the basin of attraction of this attractor, and then it will go to infinity. So, under that condition, what would you see in that system? You would see very long chaotic transient, but it is a transient. That means, after a system has undergone a boundary crisis, the chaotic attractor will become unstable. Notice, earlier when we were talking about the stability or instability of a fixed point, then we could locally analyze that. That means, we could locally take the Jacobian, we could locally look at the eigenvalues and stuff like that, we could conclude about its stability. But obviously, we cannot do that regarding the stability of chaotic attractors, because it is spread over a region. I cannot talk about the stability of a particular point. Therefore, local stability does not really apply for the stability of chaotic attractors. It has to be some kind of a global stability concept, and it is this then. That means, there would be a basin of attraction, and if that basin of attraction somehow touches the chaotic orbit, then its stability is lost. What produces the basin of attraction? What produces the basin boundary? The stable manifold of a saddle fixed point sitting on the basin boundary. Okay. So, there should be a saddle fixed point sitting on the basin boundary, and its stable manifold should be making this fellow. So, essentially it is a question of the contact between the attractor and the stable manifold of another fixed point. Okay. So, that is the what is the name? It is called the boundary crisis. So, it is, you can see that this phenomenon is therefore the handiwork of manifolds. The attractor itself is sitting on the unstable manifold of some saddle fixed point, and here is another stable manifold, and they come in contact. That is what is making the issue clear. So, these are the effects of stable and the unstable manifolds. So, whenever we will talk about the stability of a chaotic orbit, after all, you can easily understand that a chaotic orbit is unstable at every point. That is why it is chaotic. If it is stable at any point, that point itself will become stable. So, it is not so. So, within the chaotic orbit, it is unstable at every point, but it is globally stable. That global stability is indicated by this, and that global stability may be lost because of the boundary crisis. Okay. Let us now try to understand another type of interaction between the stable and the unstable manifolds. As we have already said, attractors are always sitting on the unstable manifold, right, all attractors, and therefore chaotic attractors also are sitting on the unstable manifolds. Periodic attractors are also sitting on the unstable manifolds, but the unstable manifold is not itself the attractor, right. The attractor is must be there on the unstable manifold, because unstable manifold has the attracting property, but the actual attractor may be a subset of the unstable manifold. So, there would be a large part of the unstable manifold that is not in the attractor. Attractor is only the subset. Let us see an example. For example, here we have the Henon map. On the screen, I am displaying the basins of attraction of the Henon map. But in this case, let me see the parameters that I have taken. In this case, your A, B is being varied, B is constant. So, this is minus 0.3, earlier we had taken 0.4, and A is being varied. Now, right now for this parameter value, A is 1.0, okay, and we have got a nice basin of attraction. The moment you see the basin of attraction, you would say that there must be a saddle fixed point sitting on the basin boundary. Where is it? Again, for this system, the fixed points sit on the 45-degree line, right, because y n plus 1 is equal to x n, because of that property. So, it should be somewhere on this 45-degree line. So, let us, how did we in this program locate the fixed points? Yeah, there was a command I, which if you initialize the point, its image is also shown, and you have to pull them so that they merge, they converge. So, I have the small cross which I am moving, and there is a big cross which is moving as a result. Can be seen probably, right? And I anticipate that to be, that fixed point to be somewhere in the left hand corner. So, I will bring it down and then we will go to the left. Okay, let me go to the left then. As a result of which, the image has taken a sharp turn and moving fast. Can you see that? And moving quite fast. Okay, we have done well. We are more or less at it. Yes. Okay, reasonably close. Somehow the resolution of this computer is not matching. So, let me bring the resolution a little more down. Achha, so, I will change the resolution to okay. So, I am sitting there. Now, what I want to plot the unstable manifold to the right. So, U R. Can you see the structure of the unstable manifold? It starts from here. Can you see that? And it goes, turns around, and the fixed point is sitting somewhere here. Okay, fine. So, you see here is a turn that is coming very close to this. This is what? Stable manifold. This is what the stable manifold. So, it is not difficult to anticipate that as you change the parameter further, at some point of time it might intersect. Now, what would your anticipation say? What will happen then? What did we say? If the stable and the unstable manifold intersects once, it must intersect an infinite number of times. Okay, we have proved that. So, let us see what is the result of that. As we change the row further, I will come to 1.3 maybe. So, you can see the fixed point is sitting here, there is a period 2 orbit sitting here, and now let me recalculate the position of the fixed point. It must have moved a little because I changed the parameter. Okay, now I fine. So, I am here. Let me now draw the unstable manifold to the right. Can you see? Can you see now the structure? Started from here, but has come precariously close to the basin boundary, but it is still a periodic orbit. The orbit is still a periodic orbit, right? We saw that it is a period 2 orbit here, sitting here. Good. Now, let us increase the parameter slightly. It was 1.3, let me make it 1.35. Okay, small increase. Let me increase the basin resolution. Let me make it little larger. Basin resolution let me increase, because without the high resolution it will give problems. See, it has become a fractal structure. How did it come about? Let us locate the fixed point again. Now, I will draw the unstable manifold to the right. Okay, you see, it has intersected, and as a result it must have intersected at an infinite number of points. So, as this intersection happens, you can easily see that immediately the structure of the basin boundary becomes fractal. Okay. So, this is another kind of very interesting nonlinear phenomenon that is caused by the interaction of the stable and the unstable manifolds. Clear? And these things have interesting implications in engineering systems also. For example, there is a group in UK who showed that there are situations where the people who work on naval architecture, they try to study the ship rocking motion in the sea. So, what they did was, if you have a ship perfectly there in the sea, then it is more or less similar to a pendulum, right? Because its center of gravity is down there and its point of suspension can be assumed to be somewhere up there, and it is being, suppose it is being continuously hit by waves, and waves can be a sinusoidal excitation. So, you can easily approximate it by a sinusoidal excitation. So, it is nothing but the problem of a simple pendulum being excited by a sinusoidal excitation. They found that if the magnitude of the excitation, that means a sin omega t, that a term, if it is slowly smoothly increased, then normally there is a periodic orbit, it will rock like that, there is a periodic orbit, and it will have a basin boundary. And then if you keep on increasing the wave intensity, then from the basin boundary there are fractal fingers that get in, so that while rocking in the wave, if the state somehow hits the basin boundary, the state capsizes. the ship capsizes. So, it is not a very simple action. It is, even in this simple system, there is a lot of nonlinearity because of the, because if you write the equation, it will be, can you imagine what the equation would be? X double dot plus a damping term x dot plus a some constant is equal to a sin omega t, that is it. So, even in this kind of simple systems, interesting behavior can be seen, but essentially the point is that the basin boundaries, if they are fractal, then that has a lot of implication in engineering systems also, because we want to ensure that the state does not hit the basin boundary. Okay. If the basin boundary becomes fractal, what is the concept of the basin? That if I start from here, I will land into the actual attractor. If it becomes fractal, then what? Then if you are, say, look at my cursor, yeah, if you are, say, somewhere here, see, you are normally inside the basin of attraction of the attractor. Remember, this is not the attractor, this is the unstable manifold. The attractor is a periodic attractor sitting somewhere here. So, if you are somewhere here, you would expect that I would normally go to the attractor, but you can see there is a finger of the attractor at infinity that has come inside here. And if it is a fractal structure, then if you say that my initial condition is somewhere here, obviously you cannot specify the initial condition accurately, there will be some kind of error, and within an error ball there will be a finger of the basin of attraction of the other attractor coming into that region. You get the point? So, even if you believe that I am safe, you are not safe. These kind of very typical nonlinear phenomena happen in such systems, in nonlinear systems. These are typical nonlinear phenomena. Completely, you cannot really understand this kind of phenomena, this kind of events using linear systems theory. These are typically nonlinear effects. Got the point? There have been a lot of work trying to find out, supposing there is a error ball, depending on the error ball, there have been people who proved that there should be some points of both the attractors in that error ball. What is the probability of finding your state really within the basin of attraction of the attractor that you want to go to? Those studies have been done, but essentially the message is that near the boundary where the structure is fractal, it is extremely difficult to place your initial condition in such a way that you can guarantee that you will reach that attractor. Okay. Now, let us try to understand another phenomenon. Another phenomenon caused by interior crisis. Another phenomenon called interior crisis, which is caused by interaction of the stable and the unstable manifolds. In order to understand that, let us okay, where to start? Supposing there is a attractor somewhere here. I mean, arbitrarily I am drawing a chaotic attractor, but nevertheless you can assume that. And then there is a saddle fixed point sitting here. That saddle fixed point could be a period 1 saddle, could be a period 3 saddle, could be a period 2 saddle, could be a period 5 saddle, whatever, but a saddle fixed point sitting here. What do you mean by period 5 saddle? What do you mean by period 5 saddle? If it is f x n is x n plus 1, if you take the fifth iterate, that means f 5 of x n, then it is a saddle, means this function will have an eigenvalue that is less than -1 or greater than +1 real. So, here is a attractor, here is an attractor, and here is a saddle fixed point which must have its stable and unstable manifolds. Okay. keep this picture in mind, and with that let us try to understand a theorem called, it is a lemma called lambda lemma, the lambda lemma. That lemma says that if you have a saddle fixed point and its unstable manifold and the stable manifold like this, and suppose, let me extend it a bit, yeah, suppose some line L intersects the stable manifold, some line, whatever it is, then if you iterate this line with the map, that means this is the stable and unstable manifold, the fixed point of a map. If you take the same map and iterate all the points on this line, then ultimately the line will converge, this line L will converge onto the unstable manifold of the fixed point. So, what will happen? It will, in the next state it will go somewhere here, next it will go somewhere here, and it will ultimately it will converge. Why? Because of the action of the stable manifold. Because here is a stable manifold, anything that intersects the stable manifold will come under the influence of the stable manifold, and as a result forward iterates of L will make it converge onto the unstable manifold. So, you would say the f n of L limit n tends to infinity will converge onto that. Now, what is the implication? Let us get back here. Here is stable manifold of this, and here was an attractor. Suppose at some point of time this attractor moves as you change a parameter and makes contact with the stable manifold, then what will happen? So, here is an attractor. Imagine it taking the position of L, that line. So, as it makes contact, what will it immediately imply? It will immediately imply that forward iterates starting from this orbit will converge onto the unstable manifold of this fellow. That means, wherever this unstable manifold goes, the attractor will immediately go there. Okay. Which means that earlier the attractor was small, only this much, and suddenly you will find that beyond a critical parameter value, what has actually happened, you do not see that, because you do not see these stable and unstable manifolds all the time. These are hidden in the dynamics, but underlying phenomenon is this, that the attractor has made contact with the, somewhere here, it has made contact with the stable manifold, and as a result of which the whole of the unstable manifold of this saddle fixed point becomes part of the attractor. The attractor on forward iterate converges onto the unstable manifold, and therefore, the resulting attractor becomes much larger in size. This phenomenon is actually very common, and you will find that in many situations this happens. Suddenly beyond a certain parameter value, you will find a huge attractor suddenly being born. Why? Because of this. Okay. If you want to see an example, let us get back to another system, that is the, let me go to the Ikeda map. Okay. Okay, now here is the what is known as the Ikeda map. It is a map where the variable is complex variable. So, real axis and the imaginary axis that are being plotted. But in any case, essentially the thing is that it has defined a dynamical system, a 2D dynamical system that can be plotted, right. And as you can see that starting from from initial condition, it is ultimately converging onto a fixed point, right. For a parameter value, the rho was 0.5. What system is, you do not really need to know, you can easily find out, because it is a bit longish definition of the system. That, if you want, I can write it, but nevertheless, that is z n plus 1 is equal to 0.84 plus 0.9 z n exponential I 0.4 minus a divided by 1 plus mod of z n whole square. Okay. This is the essential expression of the Ikeda map, where z is a complex number, and we are plotting the x versus y coordinate, real versus imaginary coordinate. Now, this is not all that important, because you do not immediately see a way of analyzing that. There are ways of analyzing that, but I do not want you to get into this, get bogged down to this. Look at the screen. So, here we have the parameter a sitting here. So, we are just changing it, make it 0.6. It just moves, it has moved to this point, nothing happens. .7. If you want to see now what happens, let us start from a point that is somewhere here, and let us do the t. T means the trajectory plotting. See, you can see the cross. It is making all sorts of jumps, but finally it will. You can see that it's jumping everywhere. It's some kind of a structure is emerging. Some kind of a structure is emerging. A ghostly structure. I am just keeping on iterating the map. You see, it is still not converging onto anything. It is going on making its rounds on a very specific structure. Fine. Okay. Has it sufficiently emerged? Now, if I now move the initial condition somewhere out of there and say here, see now what is happening? It is a period 2 orbit. It is a period 2 orbit. So, actually the period 2 orbit is stable, and there is nothing out there, but you can still see a structure. Why? Why? Okay, that why will become clear the moment we change the parameter slightly further. As yet nothing. Okay. So, there was this thing that suddenly appeared. It is a chaotic orbit, obviously, that appeared to have suddenly appeared. It was a period 1 orbit, then you saw a period 2 orbit, and then suddenly this. How did this come? It obviously did not go through the usual sequences that I have already talked of, like period doubling cascade and all that. It did not go through that. It suddenly went into a large chaotic orbit. But the last time when we were doing it, I deliberately started the initial condition somewhere else, not very close to the actual fixed points, and we saw that it was jumping for a long time. What does it mean? It was actually doing a chaotic transient. At a certain parameter value, suddenly it appeared. Why? What actually happened was that here there was a periodic orbit, all right, but this orbit was at that time unstable. It was an unstable chaotic orbit, and at some parameter value it made contact. There is a unstable fixed point, a saddle fixed point sitting here, and the whole thing is on the unstable manifold of that saddle fixed point. At some parameter value, that attractor, which was a period 2 attractor at that time, made contact with the stable manifold. The moment that happens, the forward iterate will contain the whole of the unstable manifold. That is what has happened. If you want to see the bifurcation diagram, if you want to be convinced that really there is no period doubling cascade, just look at it. What was the parameter value we chose? We varied between 0.7 and 0.9, something like that. Okay, so let me change the 0.7 to 0.9. See, there was a periodic orbit coming. It is from the top to bottom. It is a period 2 orbit. The parameter is being varied like this, being varied in this direction. It was a periodic 2 orbit, and suddenly it becomes a chaotic orbit. Why? Because of this phenomenon. You might ask where this chaotic orbit came from. Obviously, that is a question, where did it come from? Obviously, it must have come from the kind of phenomena that we have talked about, but ultimately it became unstable. In this part, it was unstable. Why was it unstable? Because of the phenomena that we have already talked of, boundary crisis. It underwent a boundary crisis, thereby it was unstable, and at this point of time, at this particular parameter value, what happened was the period 2 orbit made contact with a stable manifold, and therefore the whole orbit became visible. Let us choose a parameter somewhere in between, say rho 0.8, and let us plot the basin of attraction. See, the basin of attraction is fine. This is the basin of attraction of the period 2 orbit. Do you see any chaotic orbit? No. So, there is no chaotic orbit. It has a nice basin of attraction. So, imagine that this is a practical engineering system whose behavior a practical designer has designed, and therefore everything is fine. One is happy that my basin boundary is far off, yet something is lurking very close. See, it was 0.8, I make 0.85, suddenly becomes chaotic. If you want to see the behavior, see, slight change in the parameter, it becomes chaotic. The basin boundary remains the same, because the basin boundary is created by a saddle fixed point, it is still there, and its stable manifold has not changed much. So, something else has happened here, that is the interior crisis. Okay. If you want to see a simple understanding of the this particular phenomenon, let us take a look at the simple logistic map. Here is the logistic map. Okay. This is the logistic map. This one I suppose you all know pretty well, but I will make it a little more darker so that you can see it clearly. Can you see now? Yes. Now, if you see this part, what happened here? You remember? It was a period 3 window created by what? A saddle node bifurcation. So, fine. We know that it is a saddle node bifurcation. So, let us blow up this part. What was the parameter value? We have done that earlier. Uh, 3.52, let me see, 3.8, let me increase this range. No, it is further. Three 3.8 to 3.9. Find chaotic orbit, and a period 3 orbit is born, undergoes right. Clear the structure? Fine. Now see that this particular event we had already explained. It was the birth of a period 3 orbit through a saddle node bifurcation. We have already done that, and this orbit also goes through the similar period doubling cascade, resulting in chaos. Okay, but it is a chaos with a small spread. Can you see that? Suddenly at this point, what happened? Can you see that just before this point it was a chaotic orbit nevertheless, but it was distributed into 3 chunks, one chunk here, another chunk here, and third chunk here, with small spread. Suddenly at this point it became whole. What actually happened? What happened was, this is also interior crisis. What happened was, here at this point, though we can see one of these lines, this line represented the node line. This is saddle node, there is one saddle bond, another node bond, and this fellow was the node. There was obviously another saddle also bond. That saddle came like this, and at this point that saddle contacted the chaotic orbit. When that happens, what do you expect? The whole of the unstable manifold of the saddle will become part of the attractor, and that is exactly what happens. Fine. But in 1D, what is the unstable manifold? Of course, we do not have unstable manifolds there. This is a one-dimensional system. It is a one-dimensional system, and in a one-dimensional system you do not expect to see unstable manifolds. But then it becomes easier to understand. Why? Because then what happens? You have let us go. Let us make it small and let us see it in it will be easier to see there. Okay, no, not this. See. Graphic analysis, yes. So, logistic map, what is the parameter value corresponding to that? This is the birth of the the periodic orbit. So, I will draw composition 3. Okay. So, this is the birth of the period 3 orbit. I have drawn x n plus 3 versus x n. There are how many contacts now with the 45-degree line? 1, 2, 3, 4, 5. And actually these are two contacts here and two contacts here, right. If you change the parameter slightly further, you see here there are two contacts, these have crossed. Okay. Now, what happens is that because of this, here there is a fixed point that was initially a stable one. Beyond a certain parameter value, that becomes unstable. As a result, you have a chaotic orbit born here, but here there is a, what is this? This is the saddle that was born. When this particular chunk crossed the 45-degree line, this was the node and this was the saddle. This could not be seen, that could be seen, but this is what underwent the period doubling cascade and became chaotic. Fine. So, when that happens, let me draw a larger number of iterates, it will be clearer. See, it is now jumping there. It is there and it is jumping there. It will get locked there. Now, let me increase the parameter a little further. See, now the whole place becomes covered. Why? Because there was a chaotic orbit created because of this, but the chaotic orbit made contact with this line, this point. As a result, anything that goes to this side, that gets thrown off to the rest of the area. So that earlier the chaotic orbit was contained within this. Let me reduce the parameter, then it will be clearer. Say 8, 7 or something like that. No, it is still large. At 5. See, it gets stuck here. Started from another initial condition, it will get stuck here. Say, if the initial condition is say 0.5, get stuck here. Okay, it gets stuck with only within this part. Increase the parameter very slightly. It does not get stuck. Why? Because this saddle point has now covered the orbit. So, because it has this slope, larger slope, a slope larger than the 45-degree line, anything that goes to this side gets thrown to the rest of the orbit. This particular phenomenon, when ported to 2D, can be seen as the fact that the whole of the unstable manifold of a saddle fixed point becomes part of the attractor. Okay. So, let us now concentrate on this, on the sheet. What we have learned? We have learned 3 particular things that are caused by interplay of stable and unstable manifolds. 1, we have learned the boundary crisis. 2, we have learned the fractal basin boundary. And 3, we have learned interior crisis. Now, these 3, mainly these 2, taken together explains much of the nonlinear phenomena that you see in practical dynamical systems. Take together with it what we have already talked of, that means the normal local bifurcations like the period doubling, saddle node stuff, these are local bifurcations and these are global phenomena. these are called crises. Because why is it crisis? Because as you can see that there was a stable manifold, there was an unstable manifold, they come close and at some point they make contact. So, all these phenomena are because of that, because something made contact with something else. It is not to be understood in terms of some local instability, like taking the local linear neighborhood of a point and stuff like that. It cannot be explained by that. It is basically something making contact with something else in all this. Now, a very common situation in practical dynamical systems is where if you draw the bifurcation diagram, you will see that there was a stable periodic orbit born at certain time. While it is born, what you can expect? Also an unstable periodic orbit being born. They are always born together. Then you have a period doubling cascade and stuff like that. While it proceeds, there can be coexisting attractors being born. How can they be born? How can a coexisting attractor come into existence? Through a saddle node bifurcation. That means, at this point there was a saddle node bifurcation occurring in the third iterate of the system. As a result, this fellow is born. As you increase the parameter further, this will also undergo period doublings, and so on and so forth. Very common thing, not uncommon at all. But then when this periodic orbit, additional periodic orbit is born, obviously in this system there are two periodic orbits at the same time existing, coexisting periodic orbits. That means they will have their own individual basins of attraction. Okay. There will be own individual basins of attraction, and then beyond a certain parameter value, if one of these attractors, say this auxiliary or secondary attractor, makes contact with the basin boundary, then what happens? This fellow simply goes off. It no longer remains stable. So, in the bifurcation diagram, you will see a small chunk and then finally it vanishes, extinguishes. You do not see it any further. Now, normally a person not equipped with the proper knowledge in dynamics would say that, okay, I do not need to worry about it any further, this fellow has gone out of existence. No, it has become unstable, but it is there. That is a chaotic orbit, this is a chaotic orbit which has become unstable because it has undergone a boundary crisis, but it is there, and it may again regain existence, regain stability through an interior crisis. So, it might happen that beyond a certain parameter value, you suddenly find that it is enlarging to this size, and it will baffle you normally. But the moment you know that these fellows were actually existing, you would say that, okay, my orbit was actually going on like this. This was the unstable part of it. The chaotic orbit became unstable, but it still existed, and at this parameter value, the actual existing and stable chaotic orbit made contact with the unstable one, as a result of which the full orbit becomes much larger. These are very common phenomena. Okay. So, two things to remember. One, whenever we draw a bifurcation diagram like this, most people forget that there is also another fellow coming like this. What is this? The unstable fixed point. In case of 2D, it is a saddle. In case of 2D, it is a saddle coming like this. And when this orbit will make contact with the stable manifold of this one, you do expect a sudden enlargement of that orbit. Okay. Not only here, the moment this fellow became unstable, it continued as a unstable periodic orbit. that one also would have the same effect. When these branches make contact with this one, you do expect a sudden enlargement of the orbit. So, this sudden enlargement of the orbits are rather common. You do expect that to happen pretty frequently. Okay. So, let us summarize. The boundary crisis makes an orbit not go out of existence, go out of stability. Normally, you would understand stability in terms of in a continuous time system, in terms of the eigenvalue going into the right up plane, in terms of the discrete time system, in terms of the eigenvalues going out of the unit circle, all this fail. So, the stability of chaotic orbits are understood by whether or not that has undergone a boundary crisis. When something undergoes a boundary crisis, remember that that fellow is still existing, which is manifested the way I showed, that if you start from an initial condition not on the attractor, it goes on oscillating for a long time in that unstable chaotic attractor. It is there, very long chaotic transient, and I have seen such chaotic transients persisting for millions of iterates. That means, you cannot simply say that I have eliminated the transient for about 1000 iterates and no, if I get it, it is there. No, there are situations where such chaotic transients persist for millions of iterates, and that chaotic transient becomes stable whenever there is an interior crisis, when the actual existing stable orbit makes contact with the unstable chaotic orbit. That unstable chaotic orbit is sitting on the unstable manifold of some saddle fixed point. Finally, how would you actually draw a bifurcation diagram like this? See, the way to draw a bifurcation diagram normally is that you start from an initial condition. Here is the parameter axis. Here is the parameter axis and here is the variable. Start from a parameter and start from an initial condition. Whatever the initial condition is, you only need to ensure that the initial condition is inside the basin of attraction of whatever attractor there is. So, if you now iterate for a long time, say 1000 iterates, and eliminate the first 900 iterates, there is a high probability. I am not saying that it is guaranteed, but there is a high probability that you would have reached the periodic orbit or whatever orbit there is. Then plot the last 100 points. If it is a periodic orbit, all the 100 points will fall in the same place. Go to the next parameter value, do the same procedure. Then you get the picture, but it is a stupid procedure. Why? Because every time you are having to eliminate the initial transient for every parameter value. As a result, the computation time will be large, which is unnecessary. A more smarter procedure would be to make the final condition of one parameter value the initial parameter for the next parameter value. That means, when you shift the parameter to the next change, you use the final condition, final variable of the last parameter value, the initial variable for the next parameter value. So, that in that case, since you have changed the parameter only slightly, you can expect the attractor to have moved only slightly, and therefore, you are now only slightly away from the attractor. So, only with a small amount of transient, these are called pre-iterates. Pre-iterates means the transients that you have to ultimately eliminate, that becomes less. So, from the next one, you could simply eliminate only 10 or so, becomes faster. But this way, you will be locked into one periodic orbit. That means, if it is like this, you will be able to see that nicely. But if there is another one being born, you will not be able to see it. Why? Because your initial condition is locked to this one. So, though that procedure is smart because it is faster, but that is that cannot detect the coexisting attractors. In order to do that, you have to start with many initial conditions. So, if say it is a 2-dimensional system, then take a rectangle where first find out this rectangle, so that all attractors will be within this rectangle. Then you need to take the initial conditions everywhere, but if you take initial conditions everywhere and do this procedure, it will take ages. So, a smarter procedure is take initial conditions on the diagonal, because if this part is divided into basins of attraction, there is always a high probability that some initial conditions, say you have taken 5 initial conditions, at least one will fall in the basin of attraction of one of them. Okay. This is how we detect those coexisting attractors. Okay. Thank you. That is all for today.